Okay, so we're going to be leaving off from where I left off in this video when I was confused about p-values, and start from here. Some things to keep in mind: number of samples from group A and sample group B should be the same. To be significant, the p-value has to be less than or equal to 0.05. If it is more than 0.05, it is not significant. There is no significant difference then. Though it might have biological significance, even if it is not statistically. Oh my god. It might have biological significance even if this is not statistically. I can't think of an example of that, but maybe there's some times where the statistic, like let's say the global warming or the carbon emissions. No, let me think. Let's say annually carbon emissions aren't significantly causing a difference in climate change, but biologically we know it is, because instead of looking at the statistics and on a small scale, we look at it over a large time period, and those it's like a cumulative effect, and it will definitely destroy the environment eventually. It's just the 1% part of it accumulates over time period. So you might be able to say 99% of the time it's not a significant difference, but 1% of the time over 100 years, you have a whole year where it's significant and destroying the environment, and you give it millions of years, and it's just actually more significant over time now, but I'm just giving an example. It's definitely significant with climate change, so that's kind of a bad example, but trying to weed my way through with some kind of example in this thing. Hopefully that makes sense. We have a paired t-test. This is when you compare the same thing or organism at two different times. So here we have the organism in 2015. Here we have the organism in 2017. Where you compare the same thing. Okay, yeah, I just said that. In order to use this paired t-test. In order to use a paired t-test, you must meet the parametric assumptions. So those three assumptions right here: independent data, normal distribution, and constant error variation across variables of interest. So you have to meet those assumptions. Meet those assumptions, but at first the assumption will not be met. What? For example, you want to look at lichen communities on branches of two dead trees. You could take two measurements from the same tree, one in 2015 and one in 2017, and compare your results using a paired t-test. ANOVA, Analytics and Variance, analyzes differences among groups, two or more groups. It will tell you that there is a significant difference in the measurements, but it will not tell you where those differences lie. Therefore, you have to perform further analysis to discover where the difference is. To be significant, the p-value has to be less than or equal to 0.05. It can only be used if the data falls on a scale of normal distribution, meaning That's one of the assumptions of parametric. Think back to the normal histogram. It looks like the relationship between the dependent variables and one or more independent variables. This is regression. Guessing this is going to be like linear regression. How well you fit on a line, I think. So this is a relationship between the dependent variables and one or more independent variables. It gives you a regression equation that's linear. Y equals mx plus b. A would be b in this case, m would be b, and x would be x. He's got that formula fucked up. I don't know why he did that. But think of y equals mx plus b. In the slope, x is just x, and b is the intercept, y-intercept. How far up on the y-axis does it cross the y-axis? That's what b is, and y is just y. So all you really need to know for this is those factors that allow you to more accurately predict something at a specific point. The data is continuous. There is no discrete groups. Linear regression implies a causal relationship. So a change in x causes a change in y. So you change this is going to change as well. Oh wait, sorry. That would proportional relationship, so that would go up as well. So you increase x, you increase y. Decrease x, decrease y. Regression is more than a correlation, which merely describes a relationship between two variables. In order to use a regression, you must meet the parametric assumptions. So dependent and independent, we need to figure that out. What in regression is y independent or is x independent? One of those has to be. So x causes a change in y. Seems like a y is dependent on the change in x, and x would be the independent part. So it seems like y depends on what x does. X can kind of do its own thing, and it's going to change the y value. Change the y value is not necessarily going to change the x value. It would depend on what the x value is on what you get from the y value. So y value dependent, x value will probably have to be independent. In order to use regression, you must meet the parametric assumptions. What were those? Let's try to lay those out without looking. You have independent data, normal distribution, and you have to reduce your errors. So you have your independent data, normal distribution, and constant error variation. Constant error variation across variables of interest. Oh, that means you want to keep your errors about the same. You still want to keep those errors down, but you want to at least keep the level of error consistent. You don't want one set of data to be 99% accurate, 1% error, and the other two be 40% accurate and 60% error. That wouldn't be a very good comparison. So you want to keep the whole 99% accurate to 1% error throughout your data that you're comparing. Pretty consistent. That's what that's saying. population growth of ants in a colony over time. So time would be here. And yeah, the x-axis is definitely that's the part that's independent. So time is independent. It doesn't matter how many ants grow. Time is going to be constant and independent of the number of ants. But the number of ants and their growth is dependent on time to increase. Sorry. So the y value is the dependent part, x value independent. We've already worked it out. So moving on, standard deviation measures how far away the data points are for the mean. So in a normal curve, and this has nothing to do with the graph I'm drawing on, just pay attention to what I'm doing here and ignore this little part right here. So let's do that. Kind of do it in blue, that way it kind of stands out from everything. But imagine you have your graph and then something like this is on there. On the blue part, just get rid of that. Let's just pay attention to only what I'm drawing in red. Don't look at the background. So, in a normal distribution, you have your mean, and it goes down the middle like that, and then you can deviate from that mean. So this is where the mean is, kind of in the middle. So you imagine if you're from here to here on this graph, the mean would be there, and your standard deviations would radiate that way. And what I mean by that is standard deviations on a curve like this. You're at your mean. From here to here would be 1 standard deviation from the mean, 2 standard deviations from the mean, 3 standard deviations from the mean. And these corresponding values, I want to say this is about 68, 64, 60 something of the, I think 68% of the data. 68% of the data falls in between 1 standard deviation. I think 75% of the data falls within 2 standard deviations, and then I'm pretty sure 98 to 99% of the data falls within the 3 standard deviation there. So this would be 1, 2, and 3. But that's how that works. What they're saying right here. Something tells you how close the data is to the fitted regression line. This is this right here. Can't see it, but it's what's called an R squared value. So if you have points like this line they have right here is the line of best fit. And then R squared would tell you how well all of these points line up to this line of best fit right here. So how do you know if your data is parametric? You can conduct separate tests and examine your data. If a histogram of your data is not bell-shaped, then your data is not normal, and it's probably not going to be parametric. because that's one of the three assumptions that have to be made. Or so that means you have skewed right. It looks like a normal. Sorry, skewed right. Skewed left. You want to have a normal distribution like that. You could conduct a variance test. An F test for equal variances, for example. If the F test, which we never did, the F test p-value is greater than 0.5, your data meets the assumptions. P-values greater than 0.5 indicate that you have no significance and you would meet your assumptions. Be careful not to confuse this p-value with the p-value from the test of interest. So fuck. Don't know what that means. They seem somewhere. They seem different. Non-parametric tests. The U test is the non-parametric t-test. The rank test is a non-parametric correlation. Similar to your linear regression line of best fit, how it fits that line. So this would be your linear regression, and this would be your best fit. Of that would be R squared. But it'd be like that. But let's say you didn't have something like that, then you would kind of R square that. Now that's a little different because it's non-linear. It's you're getting more like a logarithmic, not logarithmic, a parabolic x squared type equation going on where it's non-linear, it's exponential. But it'd be R squared of like a exponential equation. Would be the rank test. Is that right? Okay. Yeah. The Mann-Whitney U test is like a t-test, but it can be used when the data distribution is unknown or not normal. What? Whoa, oh. Come on, man. This sounds like a last resort to come up with something for a report about how you know what you're doing when you don't even know your distribution and your distribution is not normal. This is a type of non-parametric test where you really have no idea what the distribution is and your curve isn't working out. So you have that, or you have that going on and you don't have a normal distribution. You don't even know what the distribution is. Literally no idea. Is this it? Stupid. Experiments. So happy. fucking god. Spearman's rank test. What is it? Jesus. Non-parametric correlation. So you're not meeting one of those three categories, or maybe all three aren't met. It's non-parametric. Look at how the independent variables relate to the dependent variables. How do your x's relate to your y's? It does not represent or imply a cause and effect relationship, merely an association between your x and y. It doesn't say how change in x causes a change in y. It just means that there's a association between the two. So okay, we did this. We took the Fluvio data, we did the behaviors, and he gave us the statistics, and we did a t-statistic and a p-value by going online to our computers, and we calculated that, and he gave it all to us, and t-value was like, I don't know, a number, and our p-value were all less than 0.05, so there was a was there a significance? I don't really remember. Oh man, I have that somewhere, but anyways, we already know how the dynamics of all that works. If p-value is less than or equal to 0.05, it is significantly different. There's 1% significance. Mm. 1% of the time is not significant, and I think it's like 99% of the time it is. Okay, sorry. To get a big yawn in, but we could be 95% sure it's significantly different. Say the p-value is greater than 0.05. It's a p-value of 0.12. That's, would say that there is not a significant difference. It's highly insignificant, and you would support your hypothesis. It's a really low p-value, so he's got a significance. So I emphasize the biology, but report the statistics. So, in my experience, I say, fuck the statistics. And I love that. I love this part. So this is the completely different, doing quadrants. We look at the survivorship and pine tree seedlings. Survivorship curves. I was getting into that. There's type 1s. Humans, last to be old, they will slump off. Type 1, they're dying. they just die. They're guaranteed to die at that point always. And throughout their life, they steadily decrease. So this would be if we, 90%. Oh my gosh. So at this point, this time, in that age, 90% are alive. This time, the number surviving goes down. So you could say 50%, 25%. 25%, and then 0%. So it decreases at a steady rate. So apparently songbirds do this. Throughout their life, they just steadily die. You're really high so you have a lot of species dying really early. Really early on, you have under 10% surviving. And then as time goes on, you have like 2%. And then as time goes on more, you kind of level off at that 2%. Until eventually the 2% dies out and you're left with nothing. For example of this would be frogs. So frogs, they have a lot of tadpoles, and only a certain number of those actually make it to be frogs. Little froggies. Those are my frogs. So they're happy, and it's not very many of them actually make it, and then a lot of these die. So we did a 1 meter by 1 meter squared PVC quadrant. 1 by 1 meter. There's 1 meter by 1 meter. It really wasn't 1 meter, but yeah, whatever. We just kind of had that one and kind of said, yeah, 1 meter squared, it's alright. We split into 7 groups. LOL. More like a group of like 80 people. Each group sampled 10 times, counting the amount of live and dead seedlings in our quadrant. We've done it twice so far. Do it a third time soon. Follow instructions. Did it to a number of dead. Count the dead. Did that. So number alive divided by the total number. He wants to make a graph with time on one axis and the proportion alive on that axis, and get a line. At the end of the semester, we should have a survivorship curve. So we're measuring a species. It could be a survivorship curve like this, like people, or it might be a type 2, or it might be a type 1. We don't know yet. We'll find out. Oh, there's the end. Alright, so let's keep those and move on to the next topic. I'm actually going to take a nap because I've been going pretty hard on videos. Got quite a bit of study material so far. And we really wish I would have done this sooner. But not before, whatever, I guess tomorrow or tonight when I wake up, I'll start watching all these videos of me explaining it, just rambling to myself. And then it'll work out. What does draw do? Oh, I gotta donate. Oh well. Alright guys, thanks for listening, or probably just me listening. I don't know if I'll upload these, or if they'll even be helpful by the time the exam comes around, but whatever. Probably just keep them for myself, and do similar videos like this in the future, because this app is fucking amazing.